This video is an introduction to the Apollo Web Services. The Apollo Web Services give an end-user application a single point of access to multiple epidemic simulators. An end user can specify an analytic problem, which we define as a configuration and a query of results exactly once. The end user represents the analytic problem using a standard terminology, not the native languages of the simulators. We created this simple web-based end-user application to demonstrate how the Apollo Web Services work. The simple end-user application allows an end user to configure, run, and retrieve results from two simulators, an SEIR compartmental simulator running at the University of Pittsburgh and the FRED agent-based simulator running at the Pittsburgh Supercomputing Center. The simulator configuration panel specifies the time granularity and run length of the simulation, the in-sits location code of the population, the numbers of susceptible, exposed, infectious, and recovered individuals at time 0 of the simulation, the disease, and its transmission characteristics, infectious period, latent period, and reproduction number, and optionally a specification of a vaccination program intended to control the disease. A user can run one or both simulators. We select both and click the Run Epidemic Model button. This status area reports the progress of the simulators and other components involved in returning simulation results. The SEIR compartmental simulator completes its simulation quickly. We see a plot of the incidence per day and a plot of the number of individuals in each of the 4 disease states on each day. The agent-based simulator takes longer to complete, so we are fast-forwarding the video to get to the results. We again see a plot of the number of new cases per day and a plot of the number of individuals in each of the 4 disease states on each day. We also see a new comparative plot of the incidence per day predicted by the 2 simulators. And finally, a video of the spatial dynamics of the FRED simulated outbreak over time. The source code for the simple end-user application is available on the Apollo project site. This diagram shows you most of what the developer of a simulator needs to know to connect the simulator to the Apollo Web Services. The rectangle on the left represents an end-user application. On the right is the FRED simulator, and at the bottom is a relational database into which the simulator writes its results. In the middle, the 2 diamonds represent the Apollo service, which mainly functions to route jobs to simulators, and the simulator web service. To run a simulation, the end-user application invokes the run simulation method of the Apollo service with a configuration object, which includes the identity of the simulator that the user wants to run. The Apollo service then calls the run method of the named simulator web service, in this case the FRED web service, and passes the configuration object as the parameter to the run method. The simulator web service's run method first translates from the Apollo representation of the simulator configuration into the native representation of the simulator, in this example, the native FRED configuration, which is a text file. Once the native configuration has been prepared, the run method of the FRED simulator service starts the FRED simulator and returns a run ID to the end-user application. The end-user application polls the Apollo service every 5 seconds by invoking the getRunStatus method to determine whether the FRED simulation has completed. When the simulator has completed the job, it writes its output in standard format to the results database. At present, our group maintains a single results database for the two simulators that are connected to Apollo. This slide shows the schema of the results database. A key entity in the schema is the simulated population. A simulated population can have population characteristics which are specified as axes such as gender, age range, disease status, and location. The axes take values such as male and female or NSIDs, formerly known as FIPS, location codes. This schema is designed to accommodate whatever axes and values a simulator requires. The time series entity represents the count of each simulated population for each time step of a simulation. This slide shows example output for a simulation that has just 4 simulated populations, those individuals who are susceptible, exposed, infectious, and recovered in Allegheny County, NSIDS code 42003. The time series table on the right shows how the counts of these 4 simulated populations changed from time step 1 to time step 2. The terminology for the axes and values is defined by the Apollo ontology, which we describe in a companion video. The ontology ensures that values for a specific axis are disjoint. This slide shows the steps that the developer of an imaginary Acme epidemic simulator would take to connect to Apollo. The first step is to create an Acme simulator web service. At present, we offer skeleton implementations of a simulator web service in Python and Java. Using the Python implementation as an example, the Acme developer would download the simulator service skeleton and then complete the method stubs in simulatorservice.py for SOAP run and SOAP get run status. The second step is to modify the Acme simulator to write results to the Apollo results database. Finally, the developer registers his Acme simulator with Apollo. At this point, we have described all the components of the Apollo web services that a developer of a simulator needs to know about when developing a simulator web service for his or her simulator. For completeness, we next describe how an end-user application queries the results database. At present, the Apollo Web Services supports result retrieval using visualization services. Here, we use as an example a visualization service for the Gaia visualizer. Gaia is a program that takes as input the results of a simulation in text file form and outputs maps and movies of maps. When using a visualization service, an end-user application invokes the run visualization method with an SQL query and a simulator run ID. In our current implementation, the visualizer obtains the result data by directly querying the results database. The visualizer web service then returns a visualization run ID and a URL where the visualizer will write its output, a video for example. Just like when running a simulator, the end-user application uses the getRunStatus method to poll the Apollo service to determine when the visualization is complete. When the job is completed, the end-user application downloads the visualization from the URL. We plan to create a data results service as well. This service will allow an end-user application to retrieve data from the results database as opposed to visualizations of data. Similar to the visualizer web service, The data web service will specify an SQL query, and the results of that query, the data, will be available in a file located at the return URL. The Apollo Web Services also include a synthetic population service, which will be the subject of a future video. The synthetic population service retrieves a set of synthetic individuals for a given location, who in the aggregate match the age, gender, home, school, and work locations measured by the U.S. Census in those areas. The source of these data is the Cynthia synthetic population, developed by the Research Triangle Institute in North Carolina. The innovations that we are trying to diffuse into practice by developing the Apollo Web Services and the associated Apollo SV ontology are a standard language, both terminology and syntax, for representing analytic problems in the field of epidemic prediction and control, which will enhance communication among scientists, public health professionals, programmers, and computers. And a set of well-defined programming interfaces for epidemic simulators and user applications and related software systems, which, when coupled with a standard language, will facilitate interoperability among those systems. The desired impact of these innovations, which we are developing under funding by the National Institute of General Medical Science, is increased access, ease of use, and utility of epidemic simulators for research and practice. There is additional information about this open source project at code.google.com/p/Apollo.